Alright, let's go. Number 10. The Photon Sphere. In 1959, a physicist named James McDonald was not studying black holes. He was mapping the geometry of curved spacetime around compact objects, a purely mathematical exercise, something to fill a gap in general relativity's formal structure. He wanted to know where null geodesics, the paths that light must follow, would close on themselves. The question was almost administrative. It had no observational consequence at the time because no one had confirmed black holes existed. Standard physics is clear on what light does near a gravitational source. It bends. The bending follows a precise formula derived from Einstein's field equations. Light passes close to a massive object, curves slightly, and continues outward into space. This is gravitational lensing. We observe it everywhere. The rule is light bends, but it escapes. Gravity slows it, curves it, it does not catch it. Then McDonald's equations produced a radius where light does not escape and does not fall in. It orbits. Perfectly, indefinitely, at exactly 1.5 Schwarzschild radii from the center of any black hole, James McDonald's 1959 analysis. Later formalized in the 1960s by relativists at Cambridge and Princeton, shows that a photon traveling tangentially to the black hole surface enters a circular orbit from which it cannot deviate without external perturbation. The sphere is unstable, any photon slightly displaced inward falls to the singularity, any displaced outward escapes. But on the sphere itself, light circles forever. Every alternative interpretation was tested. Perhaps the orbit decays due to quantum effects? No, quantum corrections at that scale are negligible. Perhaps radiation pressure disrupts it? Photons carry no charge, they do not interact with each other electromagnetically. Perhaps the orbit itself is a mathematical artifact? It is not. The Event Horizon Telescope collaboration confirmed its existence indirectly in 2019 when imaging M87. The bright ring in that image is light that has orbited the photon sphere multiple times before escaping. If you fell toward a black hole and passed through the photon sphere, you would see, briefly, the entire history of light that has ever entered that orbit. A shell of ancient photons from sources that no longer exist, circling endlessly. Starlight from galaxies that died billions of years ago, trapped in a loop. What happens to a photon that has orbited for 10 billion years, and whether it carries any information from its origin, is a question that general relativity cannot answer. That orbit is merely unstable. What comes next has no stable orbit at all. Number 9. The innermost stable circular orbit. In 1972, James Bardeen, William Press, and Sol Tucholsky at the California Institute of Technology were not studying the death of matter. They were calculating the accretion disk dynamics of slowly rotating compact objects. A problem in fluid mechanics and orbital mechanics combined. They were filling in the equations governing how gas clouds form thin disks around dense objects. The calculation was meant to produce a neat engineering solution for astrophysical gas flows. The prediction in standard Newtonian mechanics is smooth. Objects orbit at any radius around a central mass. Move inward, orbit faster. The relationship is continuous and stable. Nothing special happens at any particular distance. You can orbit at any altitude above the surface of any object given enough velocity. But general relativity broke this at a specific radius. 3 Schwarzschild radii. Bardeen, Press, and Tucholsky's 1972 paper in the Astrophysical Journal Letters established what is now called the ISCO, the innermost stable circular orbit. At 3 Schwarzschild radii, the last stable orbit exists. Inside this radius, there are no circular orbits that do not decay. No amount of velocity adjustment, no correction, no angle of approach produces stability. Matter that crosses the ISCO does not orbit. It spirals directly inward, accelerating to a significant fraction of the speed of light, and hits the event horizon. Every proposed workaround was examined. Perhaps magnetic fields stabilize orbits inside the ISCO? Kip Thorne and colleagues at Caltech showed in the 1970s that magnetic forces are insufficient. The gravitational gradient dominates. Perhaps radiation pressure from the accretion disk itself creates a cushion? No, radiation pressure acts radially, not tangentially, and cannot restore circular stability. Perhaps quantum corrections to general relativity alter the geometry at that radius? At 3 Schwarzschild radii for any stellar mass or supermassive black hole, quantum corrections are completely negligible. The ISCO is a classical phenomenon with no quantum escape. Everything you are made of, every atom, obeys these orbital mechanics. If the Earth crossed the ISCO of a black hole, there would be no trajectory available to any piece of matter that did not terminate at the singularity. Not a physics failure, not an engineering problem, a fundamental geometric fact about the structure of spacetime. The ISCO raises an unanswered question. If no stable orbit exists inside this radius, and matter therefore falls in on a timescale of milliseconds, what information, if any, survives the crossing? Some of that infalling matter carries energy that the black hole itself gives back. Number 8. The Penrose Process. Roger Penrose in 1969 was working on the mathematics of rotating spacetimes, what physicists call Kerr metrics, named for Roy Kerr, who derived the exact solution for a rotating black hole in 1963. Penrose was not looking for an energy source. He was studying the structure of the ergosphere, a region outside the event horizon of a rotating black hole where spacetime itself is dragged so violently that nothing can remain stationary relative to distant stars. He was formalizing the geometry. He found, unexpectedly, that objects entering this region could exit with more energy than they entered with. The conservation of energy is absolute. You cannot extract energy from nothing. This is a law so foundational that violating it would require overturning all of thermodynamics and quantum field theory simultaneously. The ergosphere appears to violate it. The resolution Penrose found was that the extraction is real, and the cost is paid by the black hole's rotation. In his 1969 paper in Nuovo Cemento, Penrose showed that an object entering the ergosphere of a Kerr black hole, the region between the static limit and the event horizon, can split into 2 pieces. One piece falls inward with negative energy relative to a distant observer. The other piece exits the ergosphere with greater energy than the original object carried. The energy deficit is subtracted from the black hole's angular momentum. The black hole slows. The escaping piece gains energy from spacetime itself. Challenges were immediate. How can an object have negative energy? The answer lies in the dragging of spacetime. In the ergosphere, the definition of positive energy relative to infinity is inverted for certain trajectories. It is geometrically legitimate. Does the process violate thermodynamics? Dimitrios Christodoulou at Princeton established in 1970 that a closely related quantity, the irreducible mass, never decreases, preserving the second law. The process is thermodynamically clean. Blanford and Znajek extended this to electromagnetic fields in 1977. And this mechanism is now the leading explanation for relativistic jets in active galactic nuclei. Beams of matter and energy ejected at 99.9% of the speed of light from supermassive black holes across billions of light years. The most energetic sustained phenomena in the observable universe are powered by geometry, by the shape of time near a spinning object. The jet that carries more power than an entire galaxy of stars is not driven by fuel. It is driven by the rotation of spacetime itself. What happens when the black hole stops spinning? When all its rotational energy has been extracted, no current model fully predicts. What the outside observer sees of that spinning black hole bears almost no resemblance to what falls in. Number 7. The Stretched Horizon. Kip Thorne at Caltech in the late 1970s and early 1980s was working on a practical problem. Could black holes be described by a membrane with physical properties, resistivity, viscosity, temperature? That would simplify the calculation of electromagnetic interactions near the event horizon. The membrane paradigm, as he developed it with Richard Price and Douglas MacDonald and published in their 1986 book, was meant as a computational shortcut. A useful fiction. General relativity predicts nothing exotic sits at the event horizon for an infalling observer. The equivalence principle, the cornerstone of general relativity, requires that free-falling observers detect no local anomaly at the horizon. You cross it without noticing. Empty space. No wall, no membrane, no surface. But for a stationary outside observer, something completely different appears. Thorne, Price, and McDonald's membrane paradigm. Elaborated in Thorne's subsequent papers, and in the black hole complementarity framework developed with Leonard Susskind and John Preskill in 1993, shows that from the perspective of an observer who remains outside, the event horizon appears as a physical membrane with an electrical resistivity of exactly 377 ohms, the impedance of free space, a temperature of order the Hawking temperature, and a viscosity calculable from quantum field theory near the horizon. Infalling matter appears to spread across this membrane, thermalize, and radiate back outward as Hawking radiation over the black hole's lifetime. Every attempt to dismiss this as a coordinate artifact failed. The membrane's properties are not gauge-dependent. They produce physically measurable predictions about how electromagnetic fields behave near horizons, predictions confirmed by calculations of black hole magnetospheres. It is not simply a mathematical convenience. So the same physical event, something crossing the event horizon, appears as two completely irreconcilable things depending on who observes it. To you, falling in, nothing. To your friend watching from outside, you are incinerated, smeared across a two-dimensional membrane, and slowly radiated back into the universe as thermal noise over 10 to the power of 67 years. Both descriptions are internally consistent. Both are supported by the physics. They cannot both be literally true. How you decide which description is real depends on which side of the horizon you are on, and you can never be on both sides simultaneously to check. The resolution proposed for that contradiction is more disturbing than the contradiction itself. Number 6. Black hole complementarity. Leonard Susskind at Stanford University in 1993 was not trying to solve the information paradox. He was working on a response to Stephen Hawking's 1975 claim that information is permanently destroyed when matter falls into a black hole. Susskind, with Gerard Hooft and Laris Thorlacius, published their complementarity proposal in Physical Review D in 1993. It was meant to be a conservative resolution, a way of preserving quantum mechanics without requiring new physics at the event horizon. Quantum mechanics demands that information is never destroyed. Every quantum state evolves unitarily. The past is always encoded in the present, in principle. Hawking radiation appears to violate this. Information falls in. The black hole evaporates. The radiation is thermal, random, the information appears to be gone. This contradicts quantum mechanics at the most fundamental level. Suskind's resolution was to accept both descriptions as simultaneously true and to claim no contradiction exists, because no single observer can ever verify both. In the complementarity framework, an infalling observer carries their information through the horizon intact, experiences nothing, and, in principle, reaches the singularity with their quantum state preserved. An outside observer sees that same information encoded in Hawking radiation emitted from the stretched horizon, never actually crossing the event horizon. Both are correct. Both are consistent with the laws of physics available to each observer. Because they can never compare notes, because the infalling observer cannot send a signal back out after crossing the horizon. No physical contradiction is ever observable. The problem is that this requires the same quantum information to exist in two places simultaneously, which quantum mechanics explicitly forbids. This is called quantum cloning, making a copy of an unknown quantum state, and it is provably impossible within standard quantum field theory. Susskind argued that the observer dependence renders the cloning unobservable and therefore physically permissible. Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, in their 2012 paper in the Journal of High Energy Physics, known as the AMPS paper, demonstrated that complementarity, as stated, requires accepting either that the infalling observer is destroyed at the horizon by a firewall, that quantum mechanics is wrong, or that general relativity breaks down at the horizon. There is no fourth option. The information that makes you who you are, the quantum states of every particle in your body, may be duplicated at the edge of a black hole in a way that the laws of physics simultaneously permit and forbid. If the information escapes, it requires a structure at the horizon that would end you before you crossed it. Number 5. The Firewall Paradox. Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully at the University of California, Santa Barbara were in 2012 attempting to do something modest, audit the consistency of black hole complementarity. They were not trying to destroy it. Polchinski in particular had worked on string theory approaches to quantum gravity for decades. This was a careful technical check of an existing proposal. Quantum field theory near a horizon in the standard analysis predicts that the vacuum state, empty space, appears smooth to an infalling observer. The Unruh effect predicts that an accelerating observer perceives the vacuum as a thermal bath. But a freely falling observer crosses the horizon into what appears to be ordinary empty space. This is Hawking's and Unruh's prediction. It is derived from quantum field theory in curved spacetime. Almheri, Merolf, Polchinski, and Sully found that this prediction is incompatible with unitarity, the requirement that quantum information is conserved. Their 2012 paper in the Journal of High Energy Physics showed that if information escapes the black hole encoded in Hawking radiation, which unitarity requires, then the quantum fields at the event horizon cannot be in the smooth vacuum state. The entanglement structure required for smooth space must be broken. When entanglement between quantum fields is broken abruptly, it releases energy. The amount of energy released at a black hole horizon, if entanglement is severed at the Planck scale, is of order the Planck energy, approximately 1.95610 to the power of 9 joules concentrated in a Planck-length surface. This is what they called the firewall. Stephen Hawking responded in 2014 with a paper proposing that the event horizon does not exist as classically defined, replaced by an apparent horizon that fluctuates. He did not resolve the firewall. He dissolved the horizon and created different problems. Juan Maldacena and Leonard Susskind proposed in their 2013 paper in Fortschritt der Physik that the interior of the black hole is connected to its Hawking radiation via ER/EPR, Einstein-Rosen bridges connecting entangled particles. This has not been demonstrated to resolve the firewall in a calculable way. If the firewall exists, then the moment you cross the event horizon of any black hole, even a supermassive one with a horizon larger than the solar system, you do not experience empty space. You are struck by a wall of Planck energy radiation that disassembles every particle in your body in less than a Planck time. Whether this happens, or whether you fall through smoothly, is currently undecidable within known physics. The radiation that creates the firewall problem was itself considered impossible when it was first derived. Number 4. Hawking radiation. Stephen Hawking at Cambridge University in 1974 was not studying black hole evaporation. He was attempting to apply quantum field theory to the curved spacetime geometry near a black hole horizon, a technical project in mathematical physics meant to understand how quantum fields behaved in strong gravitational fields. He expected to find small corrections to the classical picture. He expected the corrections to be unphysical at observable scales. Classical general relativity is explicit, nothing escapes a black hole. The event horizon is a one-way membrane. The escape velocity at the horizon equals the speed of light. No signal, no particle, no information crosses outward. Hawking found that the quantum vacuum near the event horizon continuously emits real particles. In his 1974 paper in Nature and the expanded 1975 paper in Communications in Mathematical Physics, Hawking showed that the quantum vacuum, empty space, is not truly empty. It seethes with virtual particle-antiparticle pairs that normally annihilate. Near the event horizon, one particle of a pair can fall inward while the other escapes outward. The escaping particle carries positive energy, and that energy must be conserved, so it is subtracted from the black hole's mass. The black hole shrinks. Over timescales of order 10 to the power of 67 years for a solar mass black hole, it evaporates completely. The temperature of this radiation for a solar mass black hole is 60 nanokelvin, 610 to the power of minus 8 Kelvin. The cosmic microwave background is 2.725 Kelvin. A solar mass black hole absorbs far more radiation from the universe than it emits. It is, in practice, currently growing. Every stellar mass black hole in the observable universe is colder than the ambient radiation bathing it. Jacob Bekenstein at the Hebrew University of Jerusalem had already proposed in 1972 that black holes carry entropy proportional to their horizon area. This fit with Hawking's temperature. Together they form black hole thermodynamics. 4 laws formally analogous to the 4 laws of standard thermodynamics. The framework is internally consistent and mathematically beautiful. But the radiation is thermal perfectly random. And perfect randomness carries no information. If Hawking radiation carries no information and the black hole eventually evaporates entirely, then everything that ever fell into it, every book, every person, every quantum state is permanently destroyed. This violates quantum mechanics. If the radiation does carry information, it must be non-thermally encoded in a way that no current theory can calculate, and the Firewall Paradox follows. The radiation that should resolve the information problem is, itself, the source of the deepest problem in theoretical physics. And a solar mass black hole will not finish evaporating until a time so far in the future that the word future loses operational meaning. The paradox that radiation creates has a formulation that predates the firewall by 3 decades. Number 3. The information paradox. Jacob Bekenstein at Princeton University in 1972 was working on the thermodynamics of black holes, specifically whether the second law of thermodynamics could be preserved when matter fell into a black hole. If a hot gas fell in, did the total entropy of the universe decrease? The black hole absorbed the gas and appeared featureless. Where did its entropy go? Bekenstein's question was thermodynamic bookkeeping, not quantum gravity. Quantum mechanics is deterministic at the level of quantum states. Given the complete quantum state of a system at any moment, Schrödinger's equation evolves it forward. And backward, exactly. No information is ever lost. The past is always recoverable from the present in principle. This is unitarity. It is not optional within standard quantum mechanics. When Hawking derived his radiation in 1974 and 1975, he found that the outgoing radiation is exactly thermal, drawn from a Planck distribution with no additional structure, no correlations, no encoding of what fell in. This was the information paradox. Everything that ever fell into a black hole, every quantum state, every particle's spin and position and momentum appeared in Hawking's calculation to be converted into featureless thermal noise. The final state of an evaporated black hole is radiation indistinguishable from the radiation produced by any other collection of matter of the same mass. The history is erased. John Preskill at Caltech maintained throughout the 1990s that information must escape. Stephen Hawking and Kip Thorne argued in a formal 1997 bet that information is genuinely destroyed. In 2004, Hawking conceded the bet based on arguments from the AD-S-CFT correspondence, a mathematical duality developed by Juan Maldacena at the Institute for Advanced Study in 1997, published in the International Journal of Theoretical Physics, which suggests that a gravitational system in anti-de Sitter space is equivalent to a quantum field theory on its boundary, and therefore unitary. Hawking accepted that information must escape, but could not show how. The how remains completely unknown. No calculation in quantum gravity, not string theory, not loop quantum gravity, not any other framework, has produced a derivation showing how the information encoded in infalling matter is re-emitted in Hawking radiation. Ahmed Almheri's 2019 work in the Journal of High Energy Physics, using replica wormholes and the island formula, suggests that the Page curve, the entropy curve of Hawking radiation that unitarity requires, can be reproduced. But extracting any single bit of infalling information from the radiation remains computationally intractable. Every quantum state that defines you, every configuration that makes you distinct from the rest of the universe, would be converted to thermal noise if you fell into a black hole. Whether that conversion is reversible in principle or permanent is a question that the most advanced theoretical physics of 2024 cannot answer. What the outside observer sees while this paradox plays out involves a complete freeze of time itself. Number 2. Gravitational time dilation at the event horizon. Irwin Shapiro at MIT was in 1964 working on radar ranging experiments, measuring the travel time of radar signals bounced off planets to test general relativity's predictions about signal delay in curved spacetime. His interest was in small corrections to timing due to the gravitational field of the Sun. His 1964 paper in Physical Review Letters introduced what is now called the Shapiro delay, the empirically confirmed slowing of signals passing near massive objects. Special relativity permits time dilation between moving reference frames. Clocks moving fast run slow. General relativity extends this to gravitational fields. Clocks deeper in a gravitational well run slower than clocks higher up. This is confirmed in GPS satellites. The onboard clocks run 38 microseconds per day, faster than ground clocks due to their weaker gravitational position, a correction that must be applied constantly or GPS navigation fails. The principle is unambiguous and tested. At the event horizon of a black hole, the time dilation factor becomes infinite. The Schwarzschild metric, derived by Carl Schwarzschild in 1916 while serving on the Eastern Front, published in the Proceedings of the Prussian Academy of Sciences that same year, predicts that a clock at rest at the event horizon runs infinitely slowly relative to a clock at infinity. From the perspective of a distant observer, an object falling toward the event horizon appears to slow asymptotically. It never reaches the horizon, it redshifts. Its signals arrive at longer and longer intervals. Eventually the object freezes, visible as a dim, infinitely redshifted image, and fades below detection. But it never, in finite time measured by the outside observer, crosses the horizon. Every alternative interpretation was formally tested. Is the freezing a coordinate artifact? The Schwarzschild coordinates are singular at the horizon, but Kruskal-Shekaris coordinates, developed by Martin Kruskal at Princeton and George Shekaris at the University of New South Wales in 1960, remove the coordinate singularity and confirm that the infalling observer does cross in finite proper time, but in Schwarzschild coordinates, which correspond to the experience of the outside observer. The freeze is real in the sense that no signal ever arrives from beyond the horizon. The person falling and experiences nothing abnormal at the horizon. They cross it in finite time by their own watch. But every signal they send after crossing arrives at the outside universe only at infinite future time. Their last wave goodbye, sent 1 microsecond before crossing, takes infinite time to reach you. Someone you watched fall toward a black hole, they are still there, frozen to your future light cone, forever. Whether they are simultaneously beyond the horizon is a question that general relativity answers with yes, and physics has no framework to reconcile both answers. Before any of this can occur, tidal forces would have already settled the question in the most physical way possible. Number 1. Spaghettification. John Michell, the English natural philosopher, proposed in 1783 in the Philosophical Transactions of the Royal Society of London what he called dark stars, objects massive enough that light could not escape, as a purely Newtonian exercise in escape velocity. He was not studying tidal forces, he was calculating what gravity does to photons. The tidal force consequence of extreme mass concentration came much later, when relativistic compact objects were first seriously considered by Robert Oppenheimer and Hartland Snyder in their 1939 paper in Physical Review on continued gravitational contraction. They were studying what happens when massive stars exhaust their fuel. Tidal forces near the resulting objects were a secondary consequence, not the focus. Tidal forces arise from the gradient of gravity, the difference in gravitational acceleration between the near side and far side of any extended object. They are what make the ocean bulge on both sides of Earth under the moon's gravity. At ordinary astrophysical distances, they are subtle. The rule is that they scale as the inverse cube of distance from the source.